Okay, welcome back. I think this will be the fifth lecture that we'll be going through, and we're going to be wrapping up the Conjugated System chapter 16. And the last reaction that we're going to talk about is what's known as a Diels-Alder reaction. So that's what we're going to be focusing. Whoops. Would help if I get onto my pen here, right? So Diels-Alder. All right. So let me make a couple quick comments before we kind of launch into it here. So the Diels-Alder reaction has always been kind of an oddball for me in terms of teaching it for the OChem 2 class. There's a couple reasons. What I want to say, first of all, it's actually a very, very, very important reaction, especially in the synthetic world. So if we're talking about pharmaceuticals or natural product synthesis or any of these areas that are heavily focused on synthesis, Diels-Alder is actually extremely important. And there's a couple reasons for this. What we're going to find out is that a Diels-Alder reaction will yield a cyclical system. So you can take linear systems, acyclical systems, put them together in a certain way, and we can make a cycle out of it. So that's actually pretty darn important. A lot of reactions that make cycles, especially cycloalkanes, are actually very, very, very useful for us to construct larger molecules. Maybe as an example, if you wanted to go through and look at to pick a number, the top 10 top selling pharmaceutical drugs in the last year, take a look at how many cyclical systems are present in those, right? So being able to construct those and build those and control them, that's very important, and the Diels-Alder offers a fantastic way of doing that. Additionally, the Diels-Alder reaction also has the potential of adding up to 4 stereocenters in a reaction, and that's huge, right? So again, if we're going back to, let's say, the biological focus, take a look at, again, some of these pharmaceutical agents and their chirality, right? And typically, only one enantiomer, is kind of what is the correct key to work in our bodies. And so, but we have to be able to generate a chiral center, okay? And it's not always easy to do, and you have to have certain conditions, but going through Diels-Alder, we can generate up to 4 of them depending on what we put in. And that's huge also, although it does come with some problems also if you think about it, right? So 4 chiral centers, each one can be RNS, right? So we can quickly get to a mess. However, there are aspects that we can control with the Diels-Alder there also, okay? So there are a lot of positives with it. And I don't want to diminish this. I'm not saying it's useless or any of this kind of stuff, but it's such an in-depth topic, and we give it, I don't know, what are we talking about here? I think we talk about it for, let's say, 10 pages basically is what it is. So we really, and even that, is kind of a little bit of an exaggeration. So we don't end up talking about all that much in detail here. And so we tend to gloss over some things with it, and I'm okay with that. And that's kind of what I wanted to impress with you guys here, right? We're going to be we're going to be skimming the surface with this, and I'm going to cut back a little bit also on what the book even talks about. Just because I feel, again, if this was a course for the majors only, or if we were doing an advanced synthesis, I'd be approaching this a little bit differently. But if I just want to introduce you guys one of these important reactions in making heterocycles, then I think we can kind of simplify this a little bit, okay? If you are interested in this stuff, and especially if you are a chemist or going on into some field that this would be important for you, pharmaceuticals, maybe even, take a look at the information out there, right? There are a billion websites with a lot of very good information about Diels-Alder and the modifications and the improvements and all this kind of stuff we can do with it, okay? So that all being said, right, and kind of that in the context of how I'm going to present this material, let's give the generic explanation or the generic kind of reaction for Diels-Alder. And so this is what it is, okay? A Diels-Alder takes something that looks like this. Let me draw that a little bit better so we can, I'll do it a little bit bigger here just for emphasis sake, okay? We will call this a diene, okay, so a diene, which is a word that's rife for humor. Right there you can see these shirts that say, I'm dying as I'm taking organic chemistry, ha ha ha. Okay, anyway, that being aside. So in the context of what we learned about in this chapter, right, that is a conjugated pi system. Okay, so that's a conjugated pi system. We talked about the orbitals, and that's going to be the key part when I show you guys the quote mechanism for this. Okay, so we have a diene. if I take my diene and I'm going to mix it with something called a dienophile, and you know, let's put this in, green sounds good. Diene and a dienophile, okay? So diene, oops, I think I added an extra dienophile. There it is, okay? So a diene and something that wants a diene, right? Dienophile, right? You put those two together and we heat this up, okay? So we heat this up to a certain temperature, not too hot, but not too cold, right? We make the proper porridge there, so to speak, right? And what we end up doing, let's add some color here for some argument's sake. And hopefully you guys can figure it out without me having to say 500 words, because a properly formed picture can speak a lot louder than 500 words that I say here, okay? So do you guys see what's going on here, right? So we have our diene, our dienophile, we heat this up. We make our bonds because of that increased heat there, okay, all right, hopefully you're following along with that. And there's our original dienophile, and there's our original diene, okay? So let's pause real quick and think about what we did, right? We have 1 pi bond, we start out with 2, 3 pi bonds here, right? So we lose 2 pi bonds, but we gain 2 sigma bonds. That's a good trade, right? Energetically speaking, right? We will release energy by making those sigma bonds, right? So that's something that's positive there, okay? And we ended up making a cyclohexane ring. Perfect, okay? So that's what I was talking about there. We make a ring system. If we had components on any parts of the diene or the dienophile, we would start to introduce to an extent, right, stereo centers and all this kind of stuff that goes along with it, okay? But this is the generic setup for what the products will always look like when you make when you do a Diels-Alder reaction. You will always have a cyclohexane ring with at least 1 pi bond in there. Of course, it gets a little bit more complex as we have more things around there and all these kind of things, and you know, we'll talk about that a little bit as we go through, all right? But always look for that cyclohexane ring with a pi bond, and that'll kind of be a clue. Aha, I did Diels-Alder. If I know I did a Diels-Alder, then I have to have a diene, I have to have a dienophile around, okay? And on paper, this will work, right? And there it is, although we need to improve this a little bit, right? We need to talk about this a little bit and some of the details with it, okay? Now, to make a ideal situation for the diene, we want to have an electron-rich, okay? So we want to have an electron-rich diene, and this is going to be important, right? So for those of you guys who are already zoned out and you're tabbed over to another window there, whatever, just come back, okay? This is an important topic, okay? Because I'm going to take this topic, and when we go into the next chapter, when we're dealing with aromatic systems, we're going to have to understand what we mean by electron donating, electron withdrawing, electron rich or electron poor systems, okay? So there are a set of functional groups that we consider electron donors, okay? And so what I mean is, if I put certain groups on my diene at any position, right? So if I pick, just for argument's sake, right, if I take any of my 4 carbons, okay, any of my 4 carbons that are in my diene, and I add specific functional groups to them, it will change the energetics of that conjugated system to where we could consider it electron rich, right? It would have more electrons kind of floating in the soup, so to speak, okay? So how do I make something electron rich where we're going to use a very, sorry, I don't know why that didn't zoom quite properly there. We're going to use a very odd technique called resonance, okay? Okay, now we've talked about that a million times at this point, okay? So resonance to push electrons E minus right onto pi system, okay? And I'm specifically using vague terminology because, again, I'm trying to relate this specifically to Diels-Alder, but I'm also trying to introduce you to an important topic that we have coming up, okay? So I'm going to be able to use resonance, okay, to draw a structure, to use resonance structures to push electrons into my pi system, okay? So if you think about this, and if you stop, and again, I hope you guys are always doing this, you know, as soon as I make a statement, you should go, right, you know, I don't know about this guy. He's just some dude on YouTube who's recording something. I don't even know if he's got his doctorate. I better go double check to make sure that he knows what he's talking about, right? And I hope you do, right? Because remember, me sitting here and yammering on to you guys, I hope is useful, right? But you guys digging into the book, right, and figuring it out and Googling and whatever you guys need to do, that's where the learning really happens, okay? So you guys kind of digging into that's going to be extremely important. So when I make a statement like this, see if you guys can kind of interpret or what I mean here, right? So think about it. What is a resonance structure, right? What is a resonance structure? Now, I'm going to use my magic professor powers to reach through the video camera here that I'm recording with and dig around in your brain for a second, okay? So I'm going to use my magic professor powers to say that you, as a student, would not have made it this far in organic chemistry if you did not know what a resonance structure is, okay? If you have magically made it this far, send me an email, I'll send you, I don't know, a coupon to Starbucks or something, because that is impressive that you would have made it this far, okay? But think about this. What are we doing with a resonance structure, right? A resonance structure is a situation where all the atoms remain in the same place, but we're moving electrons around. I can turn a lone pair into a pi bond. I can turn a pi bond back into a lone pair, or I can turn a pi bond into another pi bond, okay? So that's really all a resonance structure is. And of course, there's limitations with it and all this other kind of stuff that comes along with it, right? But I'm going to take a lone pair and push it into a pi system. And if you go back and you look in the book and what I talked about briefly on the last video there, we talked about orbitals and being able to talk with each other and the overlap of those orbitals and making a giant system of pi clouds, of p orbital clouds that can all overlap with each other, right? So this is kind of the idea that's going on there, right? So hopefully that all makes sense, although I'm trying to simplify this. I don't want this to turn into a 3-hour recorded video. But there's a lot of important information that's going into this very, very brief statement here, okay? But at the end of the day, what we want to do is resonance to push electrons into a pi system. And to do that, right, so as a subset of this, right, to kind of put a, I don't want to use green to confuse the dienophile stuff, so let's do black. Black sounds good, okay? So what I do then is look for, right, look for functional groups. With lone pairs, right? So LP, lone pairs, directly bound to pi system, okay? That's about as generic as I can make it this. So I'm looking for some functional groups, oxygens, nitrogens, halogens. We'll talk about those. There are a couple of exceptions, as there tend to be in all organic chemistry, right? So we're looking for functional groups with lone pairs directly bound to the pi system, okay? So to put a fine point on this, right? If I take this and I'll put Q here, okay? And don't, I can explain to you why at some point I pick Q, but it's not that important anyway, right? So if I have some functional group, it is directly bound to my pi system, okay? So it is directly bound to my pi system, and it has lone pairs on it. So let me be explicit about this. So let's say we have some kind of lone pairs on my pi system. I can then start to draw resonance structures. Let me kind of zoom in and move up here, right? For argument's sake, I could start to draw resonance structures like this, where I would end up, right, with some situation like this, right? And I should probably just, there it is, okay? So now I put an explicit negative charge into my pi system here. Everyone following along with me on that? Does it actually mean there's a full lone pair in there? No, it does not, right? Remember, resonance structures are just a snapshot of what is happening, right? It's just, we draw resonance structures all exist simultaneously to a different percentage, right? So the whole point of drawing this is saying, aha, look, now we've got a negative charge in our system, so we have some extra electrons in there, okay? Does that sound good? I hear no answers, and that's because I'm talking to myself in an empty room. All right, so anyway, so hopefully that makes sense. So we want an electron-rich diene, and I think you guys can see what the next point is going to be, right? If I have a diene that is negative, right, that means my dienophile has to be positive, right? So we want an electron poor here, right? Although we don't really call it poor, right? We call it deficient doesn't really matter. They both kind of mean the same thing in the context here, right? So electron poor, electron deficient system. So we want stuff that's withdrawing electrons, okay? So again, we're going to have to deal with something that is directly, right, bound to the pi system, and we want to withdraw electrons. We want electronegative atoms with pi bonds directly bound to that system. Right? So that's where it gets a little bit awkward. So let me give a specific example here. So one of the quintessential examples is, right, where we have some kind of carbonyl system directly bound to this. Okay, so we have some kind of carbonyl system directly bound to the dienophile. All right, and we can do the same kind of analysis, right? So I'd hope that at this point, if you guys are still with me, right, you guys would pause and say, let me see if I can figure out how having a carbonyl group bound to my dienophile would make it electron withdrawing. Because I'm asking you guys to do the same thing I just showed you there before. Draw a resonance structure and see how does it make the pi bond electron poor, right? And so we just draw a resonance structure. Let's do it, okay? Here. And then I did this in black, right? So here, negative charge, right? Okay. So now we put a positive charge where we had that pi bond before, okay? And now the world kind of makes more sense, okay? So if you guys had been with me all through Organic Chemistry 1, I would have told you on day 1 that all you need to know for organic chemistry is you find something negative and you find something positive and you put them together. I just explained to you guys, I don't know, I'd say 90, maybe 90% of what's in this textbook, right? The rest of it is you have to find the negative and you have to find the positive and put them together in a meaningful way, right? But if you're ever stuck on an exam, right, and you're like, gee, I don't even know where to start, find the negative, find the positive, bring them together, let's see what happens, right? You'll probably be on the right path. So there's my positive. Got it? So the ideal situation is we have an electron-rich diene, an electron-deficient dienophile. We're looking for the functional groups that are on there, and we bring them together in some meaningful way, okay? That is the setup for a Diels-Alder reaction. Is it always that simple? No. Right? If it was, then I wouldn't, we would be done, and I think, maybe at this point I've been going for, 10 or 15 minutes, and that would be the end of it. So let's talk a little bit about some of the specifics that come along with the Diels-Alder reaction here, right? So the best thing to do in this case is, let me just make sure I got the right colors, so I have blue and green, just to keep things together, okay? So, here is, right, a good example of an electron-rich, right? Let me change this real quick, sorry. I'll explain why in just a second. Here's a good example of an electron-rich diene. It's got 2 ether groups bound to it, okay? Those oxygens directly bound, right, directly bound there, have some nice lone pairs, okay? And you guys could go through and draw resonance and push negative charges into that pi system there, right? So, in your flashcard there, ethers, electron donating, make something electron rich, okay? And then we'll come in with maybe the quintessential example of an electron deficient dienophile, where we have a diester, right, attached to a pi bond there, okay? So now would be a good time. You guys probably already know what I'm going to say. If you've been watching all my other videos, say pause, take a look, see if you can come up with the answer, all this kind of stuff that comes with it, right? So here's something interesting, okay? Well, we'll get back to it. Maybe in the next example, I'll come back with an interesting point. So notice, however, right? Notice, however, the relative geometry of this dienophile, right? What is the relationship between those 2 ester groups there? Well, they are cis to each other, right? They are cis to each other. That is going to be retained in our product, okay? So if we start out cis here, it's going to end up as cis on our ring. If they start out trans, it's going to have this trans on the ring, okay? So we bring those 2 together. One of the key things that I always like to do is give things numbers, okay? 5 and 6. I know I'm doing a Diels-Alder, or I'm sorry, I guess I should be very specific with this. We'll heat this up. That's kind of the clue, right? Diene, dienophile, we heat this up, Diels-Alder reaction, okay? I know I got to make a 6-membered ring. Let me draw my 6-membered ring, okay? I know I have that. I know I have this. I know I make that bond right there, and I know I'm going to have that double bond right there. That's the generic name of the game, right? Now I can go back and start to fill in the numbers, right? Boy, that just kind of looks terrible. Let me make this look perfect. Oh man, that's perfection. Okay, here we go. So here's what I'm going to do, right? Was anything bound to carbon number 1? Well, no, there were just the two. There's just that one hydrogen there, right? So I don't need to add anything to that one hydrogen. Excuse me, to that one carbon right here. There was that hydrogen. We're all good to go, right? On carbon number 2, I had an ether. On carbon number 3, I had an ether. So I come back in. I will add my ether. Let me pick a different color just for argument's sake, right? So you guys can see how I'm just doing this stepwise. There's my 2 ethers. Pause. Okay. I'm on a ring, so I need to make sure I show my wedge and my dash where appropriate. Why didn't I draw this wedge and dashed? Okay. Why didn't I draw that wedge and dashed? Do you guys understand why? Right, well, what's the hybridization here? That's a trigonal planar geometry, so it's flat. I don't need to draw it wedge and dash, okay? So always remember, we're on a ring system, wedge and dash, okay? So there's carbon 2 and 3, right? 2 and 3. 4, again, only had a hydrogens coming off of it. We don't have to worry about that. 5 and 6, I have to go back and put my 2 esters. They started out cis, so I better make it cis, okay? So here, here, here. Boom. All right, fantastic. And then we could come back and continue on with whatever, the next step in our synthesis would be, reduction of the esters, or, removing the ether groups or the pi bond or whatever it might be there, right? Okay. Let me see if I can, use my magic powers here also, right? Why did I pick those as dashed, and why didn't I put them as wedged? Does it really matter? Does it make a difference? The answer is not really, okay? Because this, if I draw the mirror image of this, right? If I draw the mirror image of this, right, it's going to be the exact same molecule. I don't have to worry about chirality or that kind of stuff in this case, right? This is a hopefully you guys can see, right, there's a plane of symmetry in the middle of this molecule here, right? So this is a meso compound, right? And we can't draw an enantiomer of a meso compound. We can only draw diastereomers, but the diastereomer isn't going to form, okay? So pay attention to that. That's something that we have to talk about. If you remember how I opened this whole yammering spiel, I said that we make up to 4 chiral centers, and so we have to pay attention to those chiral centers, okay? But in this case, it's not going to be a difference, and that's why I picked the example that I did. So we have a symmetric, right? We have a symmetric diene. We have a cis dienophile. I could come back, and just for argument's sake, I'm going to do this a little bit quicker, because otherwise I'm going to lose you guys here as I continue to kind of chat away the day, right? If I did this instead, I don't like how that looked. Okay, so now I have a trans arrangement of my dienophile, perfectly fine. Electron donating, electron withdrawing. I notice it's trans, I draw my 6-membered ring, and we get to our product through the magic of having a digital tablet. I don't have to redraw everything, so I will do this, I will bring that down, and then I can just change one of these to a wedge, right? And now I've got a trans system. Now do I have to worry about, this is chiral, that's chiral, do I have to go in and, yeah, okay, right, so we make both sets there, right? Here we can have wedge and dash, here we can have wedge and dash, so technically speaking, we could just go back and fill in the blank for that here too, okay? So, does that make sense then? Right, so key part number 1, or excuse me, key part for retaining the stereochemistry here. Cis remains cis, trans remains trans, okay? Cool. All right, one more thing to talk about, and that would be if we have an asymmetric system, okay? An asymmetric system would be something like this, okay? So now we've got just one single, okay, just one single electron donating group on there. And let's say we have, sorry, I meant to do that in green to kind of maintain. And so we have one single group right here, okay? Now things get a little bit different. Now we really have to pay attention to how things come together, okay? So let me show you the, I don't know if easier way, but maybe easier way. Let me show you the easier way to do this, and then I'll come back and do a quick explanation as to why, okay? So here's the easy way to do this. There's my two starting materials. I know I'm doing a Diels-Alder. Let me draw the two potential products. The two potential products would be this comes together with this in the way that it is shown there, okay? I know, don't worry, I'll draw it out. Okay, here we go. Red, red, green, and okay, good. Or, okay, I could bring these together in another method. Okay, whoops, got a little bit, forgot my carbonyl group. Okay, so basically all I did is I flipped this in the other direction. I kept this the same, and I flipped this in the other direction. Okay, good. Okay, bring those together now. Whoops, that's there, that's there, that's there, that's there. Red, red, green. Okay? Do you guys see how these are two different products? That's the first thing. Okay? If I just start numbering at this carbon here, 1, right, 2, 3, 4. So we call this our 1, 4 product. And then this here would be 1, 3, right? So 1, 2, 3 to get to there, 1, 2, 3, 4 to get to there. Okay? These aren't numbers in terms of how we name it, right? I'm just counting how I get from one substituted carbon to another substituted carbon. That's it. Okay? These are just numbers for our sake. So this is the 1, 4 product, this is the 1, 3 product. The 1, 4 products are going to be preferred. Okay? The 1, 4 products are preferred. 1, 4s and 1, 2s are the preferred products. Okay? The difference being this. So if you guys want to pause, sit, copy this down. I'm just going to shorthand something here real quick, right, to kind of give you guys the same point. Okay? Well, I say that and then I realize, you know, that in fact it's just going to be easier to do this, so apologies for that. So let me just draw it out and then that'll be, I think, a little bit easier to kind of see. All right. Okay. That way I can talk about everything together. I'll bring these together like this, right? And then what I will have, there's this, that's burning red, right? Those are the bonds I make. There's my carbonyl. And then I have my ether group there, okay? So now we've got a 1, 2 product. With me, okay? If, so 1, 2, and 1, 4, smiley, smiley. Okay, those are the good ones. Those are the ones that tend to get formed, okay? Why or how or when or where, this kind of stuff. We have to be careful, right? And I am generalizing things quite a bit, and there are exceptions and rules, and right? But in general, if we have to pick 1, 4 is the preferred, 1, 2, but 1, 3s are not really going to get formed at all. Okay, so we have to think about this for just a little bit then, right? Anyway, so what's going on here, or how does this happen, or what's the explanation? The explanation has to deal with where we can put the negative and positive charges. Okay, so where we can put the negative and positive charges. The simple way is just draw, right? Either draw the products that you can form and find the 1, 2 or the 1, 4s. That's the easy way to do it. Okay. If you want to spend a little bit more time thinking about how this works, okay, Here's the explanation is going to be okay, so page 723, right? Oh, let me do that a little bit better. So page 723, okay? So page 723 is where I'm pulling this from, okay? So let's go back to the example that we, sorry about that. I had a little technical hiccup there for some reason, okay? So here is starting material number 1. Draw this a little bit bigger because we're going to have to really show something, okay? So there's my starting diene. Let's push a negative charge. Okay. There's my resonance. Now I've got a lone pair negative charge there. Okay. Good. Now let's do the same thing with our diene-O-file, right? So here is the example that we had, right? Or did I use an aldehyde? No, I used the ester. Okay, good. Right. So now we draw a resonance structure here also. Okay. Okay, you guys with me on resonance structures? So remember, the key thing I told you is find your negative, find your positive, and bring them together. Well, there's my negative, and there's my positive. Let's align these together. So what I'm talking about doing is just basically dragging this guy up there, right? So now the negative is next to the positive. That's going to make a bond, and then this and this here can attach, and we can do the reaction with that together, right? This is the alignment that they come together with. That's the whole point. We have to be careful because this is a bit of a contrivance also, okay? In reality, this isn't how the mechanism works, okay? But what we're saying is one of the explanation or one of the reasons we can explain this is because we can put a negative charge here, we can put a positive charge together there, and those are the ones that are going to come together with it, okay? But take a look at page 723, that's kind of where this is coming out of, all right? You can draw resonance structures, find where your positives, where your negatives are, and bring them together, all right? Cool. So hopefully that kind of makes sense with Diels-Alder there. That's kind of a very, very quick spiel with this. Take a look at some of the examples in the book. Draw your 6-membered rings, count them, number them, draw your 1-4, your 1-2s, and your 1-3s, kind of see what's the proper setup for this. Okay? Alrighty, that is essentially the end of chapter 16 for what I wanted to chat with you guys about. There are some other concepts in there that's talking about sigmatropic reactions and things like that. Again, I'm not saying that they're not important, it's just we might come back to those a little bit later, right? What I see chapter 16 is, or the purpose of chapter 16 is a direct lead-in into chapter 17, where we're dealing with electron donating and withdrawing and aromatic and conjugated systems, right? So anyway, there's your Diels-Alder and your addition reactions for conjugated pi systems, and so now we will come back in the next chapter and continue with aromatics. All right, I will see you guys next time.